And we have rotation. Unbelievable. Well, it is working. Now I want to do a simple startup test just to start an inverter. Power on, ignition on, press start button and see if the web interface shows that inverter is started. Okay, first I need to plug in the connector here. Oops. So we rearranged our power. Okay, now the crunch time. Power supply is on and apply the power. And the switch on. And it's working. As for the rest of this test, I had to reconnect to the ESP module to make sure that I have a connection to my BMOS D1 Mini, and then start inverter in the manual mode, and inverter started. Excellent, it's working. And then if I stop the inverter, inverter halted. Brilliant. My web interface is working and my inverter is starting. Today is the testing day. As I'm slightly paranoid about damaging any more things on my board or on the motor itself, I've decided to do some testing, and I'm going to be using analog discovery board which I borrowed to simulate the presence of the motor and some of the motor sensors like temperature sensors, like encoders and other things. And I'm going to be making sure that this board will work when I place it inside the motor. Let's get started. First, I hooked up analog discovery into all the signals on the connector here. I've now switched on the board. I wanted to have some form of indication that supply is present, so I decided to hook up the 5V supply to diodes 3 and 1. As digital inputs are 5V tolerant, that was a handy indication that 5V was okay. First, of course, I needed to connect to the inverter, and I decided to start from actually plotting a UDC voltage. UDC voltage is the voltage that would measure your battery, or my battery in this case, and determine if the voltage is close to target value. In this case we are looking at 360 volts. On the analog discovery I changed the UDC voltage, and as a result we can see that on the graph the voltage was decreasing as well. Great, so that part is working. Okay, I'm now pressing the start button and we can see the off mode is changing. I think it's changing to 1, so it means it's running. So now we have inverter is in operational mode. We have this little switch here which I'm gonna flick into forward mode, and now we can see the direction change to 1. Switch back to neutral, and it's switched back to neutral. Whenever electric motor is driven, the IGBT transistors switch electric current through various coils of the electric motor. So for the open inverter board to control those IGBT transistors, it has to provide PWM signal. PWM stands for pulse width modulated signal, and this signal is controlling the IGBT transistors in the inverter. So first, to test the inverter, I need to run it in the manual mode and measure PWM signal produced by the processor. I'm now switching inverter in the forward mode, and this should start PWM signals for all 3 phases. And here we go, we can observe PWM signals for high and low for all 3 of the phases we have. In the next test I wanted to check the reading of the temperature sensors. Tesla motor has a number of sensors embedded in the motor itself, and we could use DC voltage to simulate the reading from the temperature sensors in this case. By changing DC voltage levels, I'm simulating the change of the temperature, and this is reflected on the graph from the Open Inverter web interface. This is good news, the temperature sensor part is working as well. And one more test I wanted to do would be to simulate the error. So basically I put inverter in run mode. In this case I also monitor the temperatures, and I would simulate the error by pressing the button on analog discovery, and that will send one of the fault commands. In this case I pressed fault A button and inverter went from operational to non-operational mode. So the fault command is working as well. And now I will need to simulate encoders. In theory, I will have to provide a type of a clock signal on and off with certain frequency, which will give me a reading of RPM. Will it work? I'm not sure. I will try to simulate the conditions that Johannes Hubner used in this test video. Well, let's give it a try. Inverter is in run mode and we're generating 354 volts, and I would like to plot a speed RPM, and I would like to plot it on the left side. Yeah, I say start the plot, and now I'm gonna start my simulation. Again, I use analog discovery, digital input output 14 and 15 to generate a clock type of signal. So the frequency 1.2 kHz for each, and select a duty cycle of 50%, and introduced a slight delay on one of the signals. So this hopefully will simulate the encoders. And now actually it was running, so I'm stopping it, and we can start another run and see how does this change in our RPM signal. And we can see we are jumped up to 2000 RPM. That shows us that our encoder is working. Okay, so let's see if we can slightly change maybe the frequency. I'll slightly change the duty cycle, and we can see that our RPMs are actually dropped. So yeah, we are in business, we're working, and we can change RPM. Okay, next step, the throttle pedal. Some may say most important part of the vehicle. We need to test this with Open Inverter. So this is a Prius pedal. I've used that before with the Prius inverter, and no reason why I can't use it with a Tesla. Number of wires coming out of that, and in the pedal we have a Hall sensor that is measuring the angle of the application of the throttle pedal. So the Hall sensor is translating the signal into these couple of wires there. So the red wire is 5 volts, which we have to supply to the pedal, and the black is a ground, of course, to make a circuit. In this case, green and blue wire, which is the signal, wiper 1 and wiper 2. So in electric vehicles, usually quite often wiper 1 used as accelerator signal, and wiper 2 used as a regen type of signal. So basically to give a feedback for regenerative braking. Well, let's test it and see how it works. Okay, I now switched on the inverter, and I need to choose the throttle control section here. So in this case we have a single regen or dual channel. I think I want to try dual channel because I connected both wiper 1 and wiper 2 in this case, and I think the rest I will leave the same. And now I need to find the throttle values in here, and this would be those two, so the pot and pot 2 values. So I plot one to the left and another one to the right. So we now have our plot going, and we're monitoring pot 1 and pot 2. Now time to test. And we have a signal. So I release the pedal now, it's going down. And it's interesting how the pot 1, which is a red signal, has slightly different sort of rate of increase, where the pot 2 is slightly sort of delayed in a way. And they both go to about the same level. Excellent. The great result is that accelerator pedal is working as well. And the last test I would like to do is actually to test if contactors are working. So contactors are driven from these pins. I think it's pin 11 and I think it's pin 3, which is yellow white wire. And I anticipate I don't need my analog discovery in this case. So let's just give it a try. After a few experiments, I found when I switch ignition on, the pre-charge contactor will close, but when I press the start button, the main contactor momentarily close and open again. Later on, I worked out why was this happening. My theory is that we only had a pre-charge contactor working because Open Inverter board did not see the battery voltage present. And because the battery voltage was not present, it would only switch on pre-charge contactor and will not switch on the main contactor. Now I'm running the analog discovery and my computer, which will be simulating our 300 or whatever 50 volts to simulate the battery. So we put this voltage on UDC pin, and that That's what should do it, I think. So now I have switched on the power supply, and oops, I already switched on ignition, but anyway, let's try it again. So now I switched on ignition, and that should engage our pre-charge contactor. Okay, and our main contactor is open circuit, and now I press the start button, and our pre-charge opened, and our main contactor is closed, because the open inverter board does see the presence of the voltage of the battery. So that's a reason why the main contactor was not opening when I did it without analog discovery. So yeah, I was wrong. I do need analog discovery after all. But anyway, the good news, both contactors are working, and this is brilliant. So now we have our base for the Tesla board, and this is the Tesla board in here, and it was installed like this. The task is to put a Tesla Open Inverter board, which will go in this position over here. I took the approach where I fitted sensors into the PCB first without actually soldering them in, and then I could load the PCB with the sensors into the base plate mounting position and fit the fixing screws. After that, the sensors could be soldered into the board. Okay, now we can assemble the board, and we will start from checking our current sensors. It seems to be okay. So they've had to fit the board, so the two of the high voltage cables will go through these. I finished the assembly of the board, and I just needed to fit in the bracket directing the three-phase high voltage cable that's connected to the motor terminals. Installing inverter back was a very simple affair, apart from connecting the encoder cable, which was rather short. So I've decided to connect first the side which goes into the motor, and after that, tilting the inverter at a certain angle, I could connect and plug it into the open inverter board. To finish off, all I needed to do is to attach the three screws that holding the phases that go from the inverter into the motor. They had to be done quite tight, as we are dealing with the high voltage there. At this moment I hit a bit of a stumbling point, and the stumbling point is that this cable has rather unique connector that is not really easy to purchase. I've decided just to carry on with the testing by using pipe inserts. So what I found, 10mm pipe push fits can be actually fitted in this cable quite easily, and they actually really make perfect connection. Okay, I'm using pipe inserts, great decision, but how do we gonna attach the cable? I think there is not enough space for crimping, so I've decided of course to try soldering. And before I can start soldering, I need to tin with solder the edge of the pipe. Hopefully that will make my life easier when I actually start soldering the cable. It turned out I was right. Tinning the edge of the pipe did actually make soldering much easier. I quickly soldered in the connector cable for the high voltage, plus and minus, and isolated the part of the cable that was sticking out from the pipe. I have my setup here, which some people may call Heath Robinson, but for the first test I think it's gonna be okay. And this is my pride and joy. So these connectors really work well. So they plug in into the high voltage cable and fit very nicely, and only cost me about £1.20. So the rest of setup is here. So we have pre-charge contactor, main contactor, pre-charge resistor, and our famous Prius throttle pedal. At this point I think I owe you a brief explanation of a pre-charge resistor and pre-charge contactor. So why do we need a pre-charge resistor? Because we have rather big capacitors inside the inverter. When we apply the voltage, the capacitance will generate really high inrush current, and this inrush current will weld a contactor close shut. So to minimize the current, we basically put it through the resistor first, and that's why we have a pre-charge circuit. So once the capacitors have been fully charged, then the pre-charge contactor can open and main contactor can close. So in this case, the current will start flowing through the normal circuit without current limiting resistor. This red and black wires would be our 12 volt supply, So in this case it comes from my lab power supply, which is current limited, and this is the ignition switch, which turns on 12 volt supply. And this is our start button. So this is just basically momentary switch that would just apply 12 volts as you press it. And this little switch there, it's our direction switch, so it has 3 positions. So now it's in neutral, and we can go forward and we can go reverse. And now all of this cabling goes into this Molex connector, I think, if I remember correctly, and does connect into the back side of the open inverter board, which is on top of this inverter. Okay, well, it's all good talking about 12 volts, but you may ask, where is the high voltage? How do we power the motor? For this test, I'm using a contraption of 4 power supplies connected in series. So each of them is about 30 volts, and altogether that gives me about 120 volts. And for the first test, I decided to connect in the bulb connected in series to work as some sort of a protection limiting current device, as well as an indicator. The amount of glow will increase with proportion of current drawn by the inverter. Right, so now we're gonna try the first run. I am a little bit nervous, I have to say, but hopefully our bulb will work as an indicator of how things are. And I expect it to light up at the first moment during the pre-charge cycle. So once pre-charge cycle is complete, I expect the bulb to turn off. You can see that the bulb is flushed. Yeah, pre-charge is closed and main contactor is open. If I press the start button, pre-charge should be open and the main should be closed, but they both closed. What I found later on is actually the power supply was hitting a current limit. As I was rather cautious about my board, I set the current limit just below 1 amp, and that stopped from operating the contactors properly. After I increased the current limit for my 12 volts power supply and found if I pressed on a pedal, the bulb started to glow. This was an indication that we're actually drawing more current, but the motor was not rotating. But once the pedal was released, the current stopped flowing. So this is an indication that motor and inverter behaved properly. So I've decided to run another experiment with the bulb removed. Okay, I now removed the bulb, and effectively we have this connection instead of the bulb, and it goes straight into the main contactor. High voltage power supply is on. Now I'm switching the low voltage power supply. So now 12 volts is enabled. Pre-charge should be on. This should be off, which it is, and now we should press start button. Now pre-charge should be off, and it's not off, and it's still on. Something I messed up. And we have a rotation. Unbelievable. Well, that is working. So this is our pedal. I press the pedal and you hopefully can see that motor is rotating. Okay, I now solved the mystery of the contactor. It actually was not a contactor problem at all, it was just stupid me. If this contactor is closed, even this contactor is open, when I use the buzzer, it's actually picking up the resistance of this resistor and this contactor. So of course it's buzzing, but contactor itself is actually open. So how we can prove this? If we measure the resistance, but it will give us resistance of the pre-charge resistor. So yeah, that gives us pre-charge resistor, which is about 25 ohm. So if I measure the resistance of this one, so we can see it's very low, it's less than 1 ohm. So that proves that it's working. So I'm now put the motor in reverse, and it's going in reverse. Okay, now it's stopped, and I'm now going to go forward. And it's going forward. It feels rather smooth. Fantastic. Wow, the motor is working, what a relief. When I damaged the current sensors, I did not think I will ever get it to spin again. But now it's all up and running, I can move on to the next stage of the project. I hope you enjoyed this episode. Please give it thumbs up if you did. Please like and subscribe if you want to follow along, and I will see you on the next one.